Hello everyone, welcome to the new series where I'll be live solving IMO questions from different years that I haven't solved yet. And today we have IMO 2022 Part 5. I don't know, I have never seen this or tried to solve this question before, but that's the story. So yeah, I'll try to solve it right now and see how much it will take. So we need to find all triples ABP, positive integers p prime, and a to the power of p equals b factorial plus p. Um, okay, so let's start. So obviously we can say that everything depends on how a, which is greater between a and b. So for example, if a is less than or equal to b, then a divides a to the power of p, a divides b factorial, and therefore a must divide p. So a equals 1 or a equals p. If a equals 1, then we get 1 to the power of p equals b factorial plus p, which has 0 solutions. And now a equals p. So that gives us p to the power of p equals b factorial plus p, which is the same as b factorial equals b to the power of p minus p. So b is greater than or equal to p. Okay, I think sometimes in order to show that there's no solutions here, you take v2 because v2 from b factorial is it's essentially the sum of b over 2 to the power of k, like this, for k equals from 1 to infinity, and v2 of p to the power of p minus p is v2 p to the power of p minus 1, which is by LTE v2 p minus 1 plus v2 p minus 1 plus v2 plus 1, I think, minus 1. Something like that, I think. So, okay, something like that. Now let's have a think. So I think we should kind of like bound this thing with using logs. That's the like the usual procedure you do. Da, 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 da. Let's think. Okay, yeah. So okay, so this thing is greater than or equal to 2 log 2 p minus 1. So the reason is between p minus 1 and p plus 1, at least one of v2 is 1. If it's v2 p minus 1, so these both are 1, this is less 2 log 2 of p plus 1. And this one cancel out, and total is less than this. And if v2 p plus 1 is 1, then we're just left with 2 log 2 p minus 1. But this thing here is actually less than or equal to b, because it is less than or equal to b over 2 plus b over 4 plus b over 8 and so until infinity, which is exactly b. So we know that b must be greater or equal to 2 log 2 of p minus 1. which is kind of gives us a hint that B is too big. Um, yeah, so we want B factorial to be less than P to the power of P, which with this must be impossible, probably. Um, oh, wait. Yeah, I messed up slightly. This is less than equal to 2 log 2p minus 1. So this thing is less, so we need to bound this as more than equal to, I would say like b over 2 is good enough, probably. So we know that we have this. Okay, so we know that b over 2 is less than equal to 2 log 2 p minus 1, and it is greater than equal to p over 2, because b was greater than equal to p, and so p is less than equal to 2 log 2 p minus 1, which essentially rules out all p that are greater than 5, because this thing grows slower than this thing. So we just need to check p equals 2 and p equals 3. So if a equals p equals 2, then we get 2 to the power of 2 equals b factorial plus 2. So b is 2, which gives us solution 2, 2, 2. And if p equals a equals p equals 3, this would yield 3 to the power of 3 equals b factorial plus 3. So b factorial is 24, which is b equals 4. So we have another solution, which is 3, 4, 3. That's our one solution and solution 2. Okay, and that was the case where a is less than equal to b. Now let's look at the case where b is greater than a. Then we know that a to the power of p equals b factorial plus p. So b is greater than a, which means that, yeah, wait, no, less than a, less than. Okay, now it's b less than a. Uh, okay, so b is less than a, and a to the power of p is equal to b factorial plus p. Because b is less than a, then p must be greater than b. So p is greater than b, because we have p times a, it should be like approximately the same as b times b minus 1 times so on times 1. And there's only b numbers here. And since b is less than a, then every number here is less than a. So yeah, I mean, we can swap this one with a 2 or with a b, and everything will remain the same. This thing will be bigger, so like this. And if b was, if every single number is less than a, then the amount of numbers must be greater. So, okay, so it's b greater than p, b greater than p. Okay, so that's actually something like this. P is less than b is less than a. Okay, now the other thing we should notice probably is that, well, a is greater than b is greater than p, obviously. That's the first thing. But because a to the power of p equals b factorial plus p, because a was greater than b, then if prime q divides a, this prime q must be over p, or q must be greater than b for it not to divide p. Because if q is less than or equal to b, then both of these divide, so q must divide p. So this means that since we already know that a is greater than b, and then we know that this thing, and b is greater than p, then this thing is already divisible by p. So this thing is divisible by p as well. So we know that it's divisible by p. And if a is divisible by prime q, then q is greater than p, so we have already a bound, which is a greater or equal to p squared. And the other thing we also get is that because a is divisible by at least p squared, and this only by p, then b must be less than 2p. So we got two opposite bounds, so we bounded b from the top and a from the bottom, which is always good because it allows inequalities to play a role. And now we probably should just straight up get the inequalities working for us. So we know that a to the power of p is greater than or equal to p squared to the power of p. And this thing should be equal to b factorial plus p, which should be less or equal to 2p minus 1 factorial plus p. Okay, and then what should we do? What should we do? I mean, we want to neglect p, but we should do it a bit more in a more sophisticated way. We have p to p, and here it needs to show it's less than or equal to 2p minus 1 factorial plus p, and I'll say this is less than or equal to 2p minus 1 factorial, which is accurate. And we know that essentially here, the reason why I did that is because I can look at p squared multiplied p times, and here I can group the elements in the following way. I could group 2 with 2p minus 1, 2 with 2p minus 2, and then 3 with 2p minus 3, and so on. So here should have been 1, but so here should have been 1. I swapped it with a 2, and so on until we get p minus 1 and p plus 1, right? Then we just get p, I assume. But even if I got, okay, it's better to multiply by p here. I'll get 1 here. And then, so yeah, this is less than or equal to p times 2p minus 1 factorial. And then 2p minus 1 factorial, I add a p here, and we notice that this should be less than equal to, or p squared is multiplied p times. However, you know, okay, so yeah, so we see that the problem is that the product of this is less than equal to p squared, is less than equal to p squared, each product. And the reason is MGM, because if a number k is written here, a number 2p minus k is written here, and k times 2p minus k is less than p squared for the reasons that are obvious, because technically you can do this and this, which is true. And this finishes the proof. So yeah, we got that the answers are 222 and 343, which is the end of problem 5. Thank you everyone for watching and joining in. I hope this video was useful, and see you later.